Okay. Hi everyone. Hi. Great. So before we start the session, just several things. I made announcements in the course link. Did you all see the announcement? So basically, we put the assignment 1. Also, always check for the announcements in the course link. And so the deadline of the assignment 1 is October 15th, and then I will post the solution key. The first assignment will not be graded. The second assignment depends on whether they give us a TA or not. Hopefully they will. And then for the second assignment, we will make a poll whether to include it in the marking or not. And we'll do according to the majority votes. If the majority, So if the majority of the class is okay with having the assignment 2 in the marking as part of the marking, then we will do that. We'll change the marking scheme. So that's one thing. And again, assignment 1 is posted. Please do them. Do that, and don't ignore doing that because it doesn't have, for the excuse of not being graded, because that's a good example for how the taste of the midterm exam will be. And also, as I said, next week is the reading week. For the deep learning course, we don't have a class next week. So the class on October 9th we don't have a class on October 9th. Instead, we'll have one session on Friday, December 1st. Okay, so this is according to the academic calendar, and on that December 1st, which will be our last session, we will have a presentation. Okay, we will have presentation of the projects, and this will be group presentation. So for those of you who have both courses, statistical machine learning and deep learning, be careful that next week we have a statistical machine learning, because that's not in the reading week. But deep learning, we don't have it next week. Statistical machine learning doesn't have any reading week. It has we will have statistical machine learning in the next week as well. So if you are going to be busy on Friday, December 1st, make it up in your schedule. So make it free, because you need to come to the class, and that's mandatory presentation. Okay, so you need all of you guys need to be present in the class. So please free it up in your calendar, December 1st, Friday, which will be our last session, and that's the day of presentation. The same time. I need to also check with the e-access or class schedule, because I know that Friday evenings the building is closed. We need to they need to leave it open for us for presentation. That's another thing. Another thing is that I also mentioned in the announcement, you need to form teams, right? So for deep learning course, I said teams of 5 people almost. For the other course, statistical machine learning, teams of 4 people. So yeah, more or less, I mean 5. Let it be as uniform as possible. And please, you have, when was the deadline for? Do you remember? 14th? Oh, October 14th. At the end of the October 14th, please, until then, form your teams, write 1 or 2 paragraphs, several paragraphs of what you're going to do as a proposal. Proposals will not be graded. That's just for verification. And for this course, of course, the project needs to have deep learning, right? You can have also So my suggestion is that you don't restrict yourself to one of the deep learning algorithms. Try several. For example, if you are doing CNN, we'll cover. We have several CNN networks, such as RNN. So RN, you can have RNN with CNN as well, or you can have ResNet. Right? For example, for CNN, we have ResNet. We have UNet if you are doing segmentation. We also have DenseNet. So try several different structures. Also, in your project, in addition to trying several different deep networks, try different hyperparameters, try different layers, number of layers, different things, and report them and compare them, okay? And also, one thing which is very risky in deep learning, be careful not to tune your hyperparameters, such as learning rate or the number of layers and these things, by your test data and also by your train data. You have to split your data into 3 parts. In deep learning, people make this mistake a lot. They just split their data to train and test, and then they tune their hyperparameters to whatever it works well for the test data. That's cheating in machine learning. Okay, I will explain this a little bit when we cover regularization, but with more details. I have mentioned that in the statistical machine learning course, but I will cover it. So you need to split your data into 3 parts. So yeah, for projects, as I said, please form teams. And how do you find each other? In the break, in the class time. Also, you have teams, the teams group, right? You can ask each other. For seeing the list of the class, you go to your course link, there is class list, and you can see all of the other students with their email addresses. And yeah, and any question about project, presentation, about assignment, midterm exam? So on midterm exam is on October 30th, yes, and it will be in the class time. I will be present in the class, and if you have any ambiguity, you can ask and I will answer, right? So yeah, and the taste of the questions of the midterm will be similar to, not exactly, but similar to the assignment, right? So any question? No? Is everything clear? Okay, so yeah, please, the nearest deadline is the deadline of proposals and teams, right? Please form teams. And by the way, for the project, so after you submit your proposals and the teams, I will review them very quickly and will let you know my feedback. Then please start your project, and you will do the majority of your project until the last day, which is December 1st. Then present whatever you have done, the results and everything in the presentation. Then I and other students will give you feedback, and you have almost 10 days to apply the feedback and finalize it and submit the code and report. Okay, so that's the thing. Okay, thank you very much. So let's start the session. Any question about the course, about the material? No, everything is clear. Okay, so last session we ended up by explanation of gradient descent, right? And line search and these things. Then also we talked about momentum, I believe. Now we started backpropagation, but let's restart that to explain it with more details again. Backpropagation. So consider this neural network, right? And we have several layers. So by the way, sometimes they call this a layer, sometimes they call this a layer. It's not important. What is important? Mathematics, right? Okay, here for explaining backpropagation, assume I'm considering the neurons as a layer for just for the sake of notation and explanation. Okay, so as I said, it's not important. Humans' conventions is not important at all, because we might get extinct and another animal make another convention. So the convention is not important. What the underlying math is important. So layer 1, layer 2, layer 3, layer 4. And now every neuron in the neural network, we can consider it as this, right? So this is a perceptron. Do you agree? So we have these neurons, Z1, Z2 to Zm, and also AI. Do you remember? We talked about these things. AI is the summation of all of the outputs of the previous layer times the weights. So yes. So here I'm denoting the weights by X. Doesn't matter. Does it matter? Yes. Usually they denote it by W. It doesn't matter. It's just naming. You can say it as WIL or XIL. Doesn't matter. Here it is XIL. So XIL are the weights, and ZL is the outputs of the neurons in the previous layer. Agreed? Then you multiply these, and then you sum them. What is this sum? L goes from 1 to M. I mean, M is the number of neurons in the previous layer, right? So we get AI, and AI is what we have before activation function. Then we feed it to the activation function. Then it gives us Zi. So here, sigma I is a scalar function which takes a scalar as input and outputs a scalar. Why? Because we are applying activation function element-wise, right? On each neuron separately. And also, so what were we saying? Yes, see, okay. Okay, why do I say sigma I then? To be general, because what if I can apply different activation functions from in the different neurons of the same layer, right? Doesn't usually the activation function is the same, but to be general, I say sigma I for that specific neuron. And here, when I say xi1, what does it mean? The weight connecting Z1 to AI. You might say it would be probably better to say x1i, right? But for notation of backpropagation, it's easier to denote it in this way. So when I say xi1 connects the z1 to xi. So xij means that the zj of the previous layer connects to xi of this layer, right? Okay. Now let's zoom to one of the neurons, right? So one neuron has next layer and the previous layer, right? Consider layer I. So let its previous layer be layer L and the next layer be layer J, right? Here, so I'm using layer I as the index of layer. Also, when I'm going to denote the index of the neurons in the layer I by I, just for the sake of notation. So for example, when I say Zi, then AI means that the ith neuron in this layer, right? For example, AL means the 11th neuron in the layer L, right? Okay. And then we'll have summation and you will see. So ALZL is connected to AI in this layer with XIL. Do you remember I told you? XIL is the weight connecting ZL to AI. And also we have XJI connecting ZI to AJ in the J layer. Agreed? Okay. Now, what was AI? AI was summation of XIL, ZL over L, right? Over L, all of the neurons in this layer. Agreed? Sums over all neurons in the layer L. By chain rule, the gradient of this, so in in neural network, when we want to train, of course, we want to minimize some error, right? This error is also called loss function or error function. We have some error which we want to minimize. By the way, in neural network, we minimize, right? So what happens if I want to maximize something? Can you guess a scenario where we actually want to maximize something in neural networks? We have it. Can just give me some suggestions. So you're saying that maximize the distance between classes. That's a good point. We'll see that in Siamese network. We'll see that. That's one example. Other examples? Want to maximize something. Learning rate. you can bring the, so there are techniques to bring the hyperparameters in the loss function, but I'm not talking about that. So you have a simple error, simple cost, and you want to maximize that something. So let me tell you an example. When what? Mutual information. So yes, what I was going to say is in the area of probability, right? So whenever we want to increase probability, or in this case, when we are working with information theory, so we want to increase something. Usually, when we have likelihood of data, we want to do maximum likelihood, right? So we want to maximize the likelihood or log likelihood of data. So in this case, we can't have maximum. Usually in the libraries, we don't have maximization because backpropagation has gradient descent in it, not gradient ascent. Therefore, what should we do? Negative sign. So we multiply that thing with negative, it becomes cost, which needs to be minimized, right? Therefore, when we want to maximize the likelihood, we minimize negative log likelihood. The cost becomes negative log likelihood. This is the reason, okay? So we have some error, we want to minimize it. Of course, what should we do? We should take derivative of, you tell me. So we have minimization of error. This is an unconstrained optimization problem. What should we do? Derivative, what we learned in high school. The first order optimality condition, take derivative, set it to 0, right? But when we set it to 0, we can't find a closed form solution. Therefore, we need to do it numerically, and that's exactly what we do. We use first order optimization, gradient descent. So we need gradient or derivative, right? Of course, we need to take gradient of error, right, which we want to minimize, with respect to our parameters to be learned. What are the parameters? The weights of the neural network, right? So consider the weight between neurons L and I. So I mean this, okay? Consider it. So derivative of E, error, and E is a scalar, usually. The error is usually scalar. With respect to XIL, is what according to chain rule, can I write it as derivative of error with respect to AI, which is this, times derivative of AI with respect to XIL. Can I write that? So this is exactly what we have. Agreed? Now, derivative of AI with respect to XIL. See this equation. Do you remember AI was summation of XIL with ZL sums over L, right? What is the derivative of, what is this derivative? Can you tell me? AI with respect to XIL. ZL, because this is linear with respect to XIL, right? And derivative becomes ZL. But where did the summation go? Why isn't it summation of ZL over L? As you see, I have replaced it with ZL just, not summation of ZL. Can you tell me? I understand what you're saying. Yes. So let me rephrase what you said. So because when we are taking derivative with respect to XIL, it's with respect to XIL for a specific L. So let me write it down in this way so you understand better what I'm saying. Let's unwrap the summation, right? So what does it mean? This summation xi1 z1 plus xi2 z2, right? Until the last neuron. Agreed? So in the middle, okay, in this case, assume I say derivative of AI with respect to xi2, right? Then what happens? The first term becomes constant, goes away. The third term, the fourth term, all of them will come constant because they are constant with respect to xi2, right? Only the second term remains, right? And its derivative with respect to xi2 is z2, right? Now, let's consider derivative of AI with respect to xi3 becomes z3. Now, replace that with a specific L. Derivative of xai with respect to xil, it becomes zl. Did you understand why the summation goes away? Because it's the derivative with respect to xil for a specific L, right? So that's why it becomes zl. Now also I denote derivative of E with respect to AI. I denote it by delta I, right? So I replace it with delta I. So far clear? Error can be any error, such as mean squared error. So yeah, error is, assume error here is a general function that we can calculate its derivative, okay? And you can use any error. So any other question? No? Okay. No, the chain rule or partial? Well, because the variables depend on each other. Error is at the last layer, and I can't calculate directly the derivative of this error with respect to the weights. When I want to calculate the derivative of E with respect to xil, it depends on the derivative of E with respect to xji, for example. Right? That is the reason that by the way, we will see that we will have nested chain rules. We will have chain rules inside chain rules, okay? Because I think it's obvious. We have several layers. We have a lot of parameters, okay? Which one? AI, you mean? AI is a summation. Here we had it. Do you remember? So here, this is the neuron. AI is you multiply the weights by the outputs of the neurons of the previous layer, then you sum them up, right? This was in perceptron. Do you remember? Then we feed it to the activation function. After activation function, we denote it by Zi. Okay. So now let's continue. Let's continue. Now, if layer I is the last layer, so it means that then we don't have layer J, right? And the error will be exactly at the layer I, right? Then delta I can be computed by derivative of error loss function with respect to the output. But what was the delta I? Which was derivative of error with respect to AI, right? With respect to AI. Then if my layer I is at the last layer, what happens? You tell me. So either we have activation function in the last layer or we don't, right? If we have activation function, then we need to calculate this becomes derivative of E with respect to Zi times derivative of Zi with respect to AI, right? This, what is this? This is exactly derivative of error, because error function is some function, right? And what is its input? That cost function, Zi. Zi will be the input of that function. So basically, this will be the derivative of that activation function. Do you remember when we introduced the activation functions? I told you that their derivatives formulas too, right? So what about derivative of Zi with respect to AI, assuming that layer I is the last layer? So it's basically the derivative of, this is derivative of error. This is derivative of activation function. Did you understand? This is derivative. This is sigma I prime. You didn't get it? Let me recap. Let me assume I'm in the last layer. This is the last layer. Here I calculate the error E. What is error? For example, error, assume, might be mean squared error, right? Here, the input of my error cost function is the outputs of Zi's, right? So Zi is the input of my function. Then what becomes derivative of E with respect to Zi? You tell me. Take derivative of this cost function with respect to Z. Did you understand? What about derivative of Zi with respect to AI? What is that? This is the derivative of the activation function, sigma I prime. Sigma I was the activation function. Sigma I prime is that, for example, if it is sigmoid, I don't remember the formulas. I don't memorize them. So let's see, activation functions. We have it in the. You tell me. We did have it in the lecture of activation fully connected networks, but let's recap it here. So activation function of sigmoid, it's sigma times 1 minus sigma, right? So assuming that my activation function in the last layer is sigmoid, then what happens? This sigma I becomes sigma I1 minus sigma I. Agreed? Then derivative of E with respect to Zi is also obvious. For example, in this case, what is the derivative? Can you tell me? It becomes, if you calculate it, it becomes 2Zi minus Yi. Because it's quadratic with respect to Zi. Okay? So if it is the last layer, its calculation is easy, right? However, if it is somewhere in between, it is one of the hidden layers, right? Then it's not easy. We need to do chain rule. Okay. However, if I is one of the hidden layers, then delta I is computed by chain rule. How? Let's see. What was delta I? Was derivative of E with respect to AI, right? We defined it in the previous slide. Here in this equation, right? Now let's calculate it. So this becomes, again, let's use chain rule, derivative of E with respect to AJ times derivative of AJ with respect to AI. Do you see what I'm doing? Right? But why do I have to sum over J? Can you tell me? Exactly, because here I have a lot of neurons in the layer J. And as you see, AI will depend on all of them, these neurons, on all of them. Because the output of this neuron goes to a lot of neurons in the next layer. And it is impacted by all of them. In other words, if I tweak the error, it will tweak all of these, and each of these tweaks also tweaks AI, right? So in chain rule, I have to have this summation. Agreed? Now, what is derivative of E with respect to AJ? It becomes delta J according to our definition of delta, right? What about derivative of AJ with respect to AI? I repeat it here. I'm going to calculate it here. But now let's take a careful look at here. Delta I depends on delta J. Do you see? Every delta of some neuron depends on all deltas in the next layers. I think it's obvious because we are backpropagating. We are going from the last layer to the first layer, right? So every neuron will depend on the next layers. And now let's calculate derivative of AJ with respect to AI. Okay. So it's derivative of AJ with respect to Z. So let me clean this figure and let's see what it means. Derivative of AJ with respect to ZI, then derivative of ZI with respect to AI. Agreed? So now you tell me, derivative of ZI with respect to AI, this one. What is that? That's exactly derivative of activation function, right? I denote it by sigma prime AI. Agreed? And its input is AI, right? What about derivative of AJ with respect to ZI? We just talked about it according to this equation, right? So derivative of AJ with respect to Z, because AJ is this, with respect to ZI for a specific I, the summation goes away and we'll have XJI. Agree? Now, what happens? So I'm gonna replace this with this, which I just calculated. Agree? Then what happens? We know that sigma prime of AI doesn't depend on J, which is the summation. So I can bring it out of the summation. Agree? So I bring it out of the summation and I have the rest inside the summation. As you see, we are going step by step, and you need, if you didn't understand it, ask me, and you need to think about it, sleep on it. When you are rewatch what I said, if you understand it deeply, and you'll see it's very simple. It's very, and this is the simplest explanation of backpropagation. I haven't seen a simplest explanation for backpropagation than this. Okay. Which one? I didn't get your question.
Why your notes?
YE? Where did I have Y?
Yeah.
Delta, you mean? I didn't. Delta, you mean?
Why?
Y? We don't have Y here.
No.
Do I have?
Yeah, here.
Oh, here is the actual label. No, who said that? Deep learning can be used for both supervised and unsupervised learning. If we have deep learning for unsupervised learning, we will see that. For example, reconstruction autoencoder, or some of the generative models, you can see them as unsupervised learning. But actually, most of the deep learning is supervised learning. So you have labels usually.
Labels, how we define the error on
The error will be how much do I deviate from the actual labels if I assume that my output of neural network is the predicted label. So assume my output of network is the predicted label, it needs to imitate the actual labels, right? So for example, we can use mean squared error, or in case of classification, we can use crossover, cross entropy loss function. Okay. Did you get it? Okay. So this is what we found. I'm repeating it. Now let's put this equation back in equation 10. Recall equation 10. You remember we had this equation. We wanted to calculate this delta I, right? We just calculated that. Let's put it back here. So equation 10 becomes this. This was equation 10. So this becomes this, because I just replaced delta I with this, right? Now you tell me. So backpropagation uses the gradient in equation 13, this, for updating the weights XIL for all of the I's and L's, right? So basically for all weights in the neural network. And now I just calculated the gradient. This is a gradient, right? Do we have all of these? Do we have all of these? Can you tell me? Do we have xji? Yes, xji is the weight, right? This is the weight so far, because the weights are updated, right? This is the weight until the last iteration, the weight value. And we know that the weights initially are initialized to random values, and then they get updated. So we always have xji from the previous iteration, right? What about AI? We have it because we have fed our data to the network. We go so how do we calculate the error? We first feed the data to the network. We have a forward propagation going from the first layer to the last layer. Then we do a backward propagation, and we call it backpropagation, right? So we have a forward propagation and backward propagation. For calculating the error, we do a forward propagation. We have the error, and then we use this to update the weights, backpropagation, right? So we have AI from the forward propagation, right? And what about ZL? We also have it because we can apply the activation in the forward propagation. We are applying the activation functions, right? What about delta J? Do we have it? We have it. Why? Because we are going from the last layer to the first layer in backward propagation, backpropagation. Always, when I'm calculating the delta of this layer, I have already calculated the deltas of all of the next layers, right? Did you get it? Is it confusing? Did you understand everything? So I'm going from last to first layer, and at every layer that I am calculating the deltas, I need the deltas of the next layer. I already have calculated them, right? So everything in this equation is known, therefore gradient is known, right? So now I can use it in gradient descent. What was gradient descent? Simple this. The weight in the next iteration, in this iteration, is the weight in the previous iteration minus eta, this gradient. Agreed? Did you get it? So this tunes the weights from last layer to the first layer for every iteration of optimization, right? By the way, so here when I say XIL, I'm saying that at every iteration, I have a forward pass and a backward pass. Did you understand? At every iteration, right? I have a forward pass and a backward pass. And usually, we have a batch of data. We feed several data points. And then in this error, we calculate the summation of error. The summation of error. Okay, we'll talk about it this session. We'll talk about the all of these details this session. Therefore, backpropagation, which was proposed in 1986, is actually gradient descent with chain rule in derivatives because of having layers of parameters. It is the most well-known optimization method for training neural networks. Do we have other training algorithms for neural network? Do we have? Can you give me suggestions? Have you heard of other? What? CNN. CNN is a structure of neural network. We'll talk about it. We'll talk. No, I'm saying that how to train, to tune the weights of neural network for training. Of course, the most well-known one is backpropagation, nowadays used. Do we have other? Adam is gonna be used with backpropagation. We'll cover it today. But what? Least square. So least squares, what does it mean? Least squares. So that's when you minimize mean squared error. They also call it least squares error. Why? Least means minimize. A squared error is mean squared error. So two names for the same thing: least squared error or minimization of mean squared error. Okay. Also, in my statistical machine learning course, if you see that, for example, regression uses least square or minimizes a mean squared error, right? The linear regression. So let me give you some examples of other algorithms for training neural network. Search. Do search and see. So you can change the weights and see what happens to the cost, right? So some combination of the weights reduces the cost. If I do it randomly, it will be awful, right? It will be forever. I can do grid search, but it will need infinite time. Why? Because I have too many cases. Can you imagine how many weights do you have? How many permutations do you have? Even if you have a small grid, right? It will be mind-blowing. It actually needs infinite amount of time. So grid search is not good. Random search is not good. A middle case scenario, meta-heuristic search, intelligent search, right? Intelligent search. So examples, genetic algorithm, particle swarm optimization. They have used genetic algorithm for training neural network, right? So you can do intelligent. For more information on meteoristic search, just see my adaptive algorithms course in my YouTube channel. Okay, that's I have covered several algorithms in meteoristic optimization. So that's one thing. Another technique, for example, do you remember last 2 sessions ago, we talked about for simple neural networks, Hebbian learning and these things. Those are also techniques for training simple neural networks, right? Hebbian learning, or what we had for one perceptron or one Ada line. Do you remember? So those are also for training neural networks. But for complicated neural networks, one of them is backpropagation, one of them is genetic algorithm, for example. We also have others. How we learned restricted Boltzmann machine. I talked to you about the restricted Boltzmann machine. Do you remember? If we have time, we will probably cover that in this course. Okay. So that's another technique to train the neural network. So backpropagation is not the only one, but it's a dominant one, of course, right? Restricted Boltzmann machine, RBM. I think 2 sessions ago I talked about it, or last session. 2 sessions ago, when I was talking about the history of neural network, I said RBM, Hinton proposed that for training neural network, and he said in order to make the neural network deep, we can consider every layer of neural network as an RBM, right? Its main idea is that I have some energy in this layer. Let me copy this energy to the next layer, but this copying is not easy. Why? Because the number of neurons do not match. I can't just copy and paste. So for this copying, I need to do it probabilistically. Right? So you can do it, train the neural network in various ways. Now, this backpropagation can be implemented in several ways. One of them is a stochastic gradient descent. But let's first talk about the stochastic gradient methods in general. Okay. Assume we have a data set of n data points, A1 to AN. Here, A means the data point, right? And their labels, L, L1 to Ln. Again, naming is not important. You can call it a Y. Let the cost function f be decomposed into summation of n terms, right? So I have a cost function, which I can decompose it into f1 to fn. Okay. Some well-known examples are like this least squares error. Assume I have fi x is this. So for every input data ai, I have some x here minus li. So this is basically just for one, assuming that I have a neural network with one layer x here in this case. If I don't have that, then I need, if I don't, I have a complete neural network, then basically this becomes the output of neural network, right? But in this example, this means that this is a neural network with only weight x without any activation function. Doesn't matter. So I just, the formula itself and then the concept of decomposing is important to me. As you see, I am having fi. I goes from 1 to n. Also, you can have absolute error, such as this, right? AI transpose x minus li. You can have hinge loss. Hinge loss is in this form. Maximum of 0 and 1 minus this. So basically, whenever you have maximum of 0 and something, this is called hinge loss. A standard hinge loss is defined as maximum of 0 and everything. So whenever it is negative, make it 0. Did you understand? So this is called hinge loss in neural networks. We have seen it. We will see it later when we talk about triplet loss. We will see that, okay, later. But we have seen this function also beforehand. Where did we see that? What? Yeah, ReLU activation function, right? So we saw it. Also logistic function or sigmoid function, doesn't matter. So we have some FIs. The important thing is that I have some FIs which takes LIs and AIs. Here I'm minimizing this cost function. Here X is denoting the weight of my thing. By the way, here in these a few slides, I'm talking about general algorithm. It's not just for neural networks, right? I have some optimization variable, some cost f of x, and its variable is x. I want to minimize this f of x, and I can write f of x as this, right? Did you understand? So in general, not just neural network. I'm gonna then later use that for neural network. What is that? So I'm minimizing this cost function. What should I do? It's an unconstrained optimization problem. What should I do? Take derivative, as always, right? Take derivative. So take derivative of this. What happened? We know derivative is a linear operator, right? It can pass through the summation. So I will have this, right? If you understand. So basically here, the total gradient or derivative became the mean of the gradients of f1 to fn, right? The mean, right? Because my cost was the mean of the costs. And now I can put it, what was this? This was the formula for update in the gradient descent. Do you remember? So if I use this gradient as the update in the gradient descent, this gives me full gradient descent. Let's call it full gradient descent because I'm using all of the gradients, the whole gradients, okay? So this is what we had. However, sometimes this full gradient calculation of this full gradient is costful, is very costly. It needs a lot of calculation. Why? Especially when n goes to infinity and n is large, right? Then I have a big summation and I need to calculate derivative n times, right? It's hard to calculate it. In this case, they simplify it and they call it a stochastic gradient descent, also called a stochastic gradient method. What does it do? It says at every iteration of gradient descent, rather than using the whole gradient, which was this, use only one of them. Gradient of, so we have gradient of f1, gradient of f2 until gradient of fn, right? Use one of them, and which one? Randomly sample. So it's hence the name a stochastic. A stochastic means random. Yes, stochastic means random. Deterministic means not random, right? The stochastic gradient descent is because we are randomly sampling one of the gradients. So basically means take one of them, such as gradient of fi randomly, and update your solution. In the next iteration, take another random one and do it. Of course, it is approximating the solution. Its solution is not exact as exactly equal to the solution of gradient descent. It's approximating that, but it makes our calculation easier. Right? Because I don't need to calculate the full gradient. So this is called a stochastic gradient descent. Basically, it samples or bootstraps one of the points at every iteration. What do I mean by bootstrapping? In statistics, do you know what bootstrapping means? As far as I remember, do you remember we can have simple random sampling with replacement or without replacement? Do you remember? Do you understand what I mean by with and without replacement? So assume I have a bag of several points. I put my hand inside the bag. I take one of them. If I put this ball outside of the bag, and the next time I do get another one, but I haven't put that ball in the bag again, that's called without replacement. If I have the bag of balls, I take one, read it, put that back in the ball, shuffle it again, then do this. This is called with replacement, right? And they are different, right? So we have simple random sampling with replacement or without replacement. If we do simple random sampling with replacement, that's also called bootstrapping in statistics. Okay. So the idea of a stochastic approximation was first proposed in 1951. See that reference. Then it was first used for machine learning in 1998, right? So as this equation states, a stochastic gradient descent often uses an adaptive step size, eta, right? It usually uses adaptive step size, which changes in every iteration. The step size can be decreasing. Why? Because initially we are far away from the actual solution. We need to jump. So in other words, I need to explore first. Later, I need to exploit because I'm supposed to be close to the actual solution. I don't need to oscillate around the actual solution. Okay. So we can have various ways to have adaptive learning rate, such as 1/k. As you see, all of these are decreasing functions. K here is the iteration index, right? Or 1/√k. Or fixed. Here it is fixed. Okay. But a fixed step size has some flaw. If it is big, at the end will oscillate around the solution. If it is too small, then it will take forever to get to the actual solution because initially it will be very slow. Now, again, consider a convex and differential function f with domain D, okay? Here we want to talk about convergence rate of gradient descent. What do I mean? How fast do I get close to the actual solution, right? The solution. So now assume consider a function f, the cost function, which is convex and differentiable. Its domain is D, and its gradient is L smooth. I already talked about L smoothness, Lipschitz smoothness in the previous session. Okay. Let f star be the minimum of cost function, which we want to, and x star is a minimizer. Okay. Starting from the initial point x0, some random x0, and after t iterations of optimization algorithm, okay, we'll have the following: the convergence of gradient descent, not a stochastic gradient. The convergence of gradient descent is this, equation 18. What does the left-hand side mean? It means that my cost value at the position in the next iteration, in this iteration or next iteration, doesn't matter, minus f star. It means that how much my current cost in this iteration is away from the minimum cost, f star, right? Is less than or equal to the right-hand side. Of course, this left-hand side is basically kind of meaning how fast we are. Because if we get to the f star very fast, this left-hand side is very small, right? And the right-hand side is an upper bound on that. So we call it convergence rate, right? Because the lower this upper bound, the better it is. Then what happens to the right? So right-hand side, we can prove it. I have excluded the proofs here, right? Because it will be overwhelming. What is that? 2, but we will analyze it. We'll analyze. 2L, L is the L smoothness of the gradient of the function. The times squared L to norm of x0 minus x star. What was the x? So what is this? How far I am from the x star. So the left-hand side was how far is my cost function from the f star. This means how far is my position from the x star, right? Agree? And over t plus 1. T is iteration index, okay? Do you agree that it's in the order of 1 over t? Big O notation. You know what big O notation is? Big O notation is just, so consider this function. An upper bound on this function is big O notation, okay? Lower bound on the function is big omega, big omega. If I'm around this function, so basically an expected value, I'm around where I am, they call it theta. So these 3 things at least, we also have a small o, but these 3 are in complexity theory. If you have passed an algorithm course, you might have seen them. But whenever you see big O, basically, it means that it's an upper bound, okay? And I think its calculation is easy. For example, you ignored plus 1 because you're talking about order. Also, the numerator, you don't care much. Here, I care about iteration index. So it's in the order of 1 over t. Did you understand? Okay. So basically, of course, the more t I go, the less this upper bound becomes, because I'm getting closer to the actual solution, right? But how fast does it go? 1 over t. If it was 1 over t squared, it would be better, right?
Find our own cost function, a new f. So in that case, we need to prove convergence.
So can you repeat?
Yeah. So for equation 18,
Yes.
previous slide. What if? So in our research, what if we define our own cost function f, and in that case, do we need to prove the convergence of our algorithm?
No, the reason that I'm talking about the convergence rate is to compare gradient descent and the stochastic gradient descent. And usually whenever you're in optimization, as I said, these a few slides are not just for neural network, it's just optimization, right? Whenever in optimization, they propose an algorithm, they usually, first off, they prove why it converges to that solution. Also, they say how fast it is. And why am I saying this here? Because in a few slides, I'm going to compare stochastic gradient descent for you by comparing their convergence rates, and you will understand how they are different.
Yeah.
And this works for any cost function f, but it needs to be convex and differentiable function.
So when you are reviewing papers,
Yeah.
applications so do like require the authors to prove their algorithm to be convert?
Depends on what paper it is. If it is about optimization, yes, they need to prove that. But if they are using an already proved optimization algorithm, they don't need to prove the optimization algorithm. Okay. So now I'm going to talk about convergence rate of a stochastic gradient descent. Okay. Consider the function which is decomposable, right? And again, each of them, which is bounded below, it means that it doesn't go to minus infinity. And each fi is differentiable, and that the domain of function fbd, its gradient is also L smooth. We also need this assumption because of the proof of this convergence. So it's just expectation of L2 norm or squared L2 norm of the gradients with conditioned on x is less than or equal to beta squared, where beta is some constant. Okay. Now assume having this, depending on the step size, we have different convergence rates. Okay, for a stochastic gradient descent. Again, accept it without proof from me. Okay, so if it is 1 over tau, here is the iteration index. Right? T also is iteration index. Then the convergence rate is in the order of 1 over log of t. Okay. If it is 1 over square root of tau t, then the convergence rate is on the order of log of t over square root of t. If it is fixed, it's this. Okay. And we are going to analyze that. If the functions are mu strongly convex, what do I mean by strongly convex? Do you know what is the difference of convex? So this is convex. This is also convex. Do you agree? But this is strongly convex, but this is not a strongly convex. Why is it important in optimization whether the function is strongly convex or not? Because if it is strongly convex, it has only one global f star and one global x star. If it is convex, not strongly convex, it might have several x stars, but one f star. Because in each of these, the function is minimized, different x stars, all of them has one f star. Did you understand? That's the reason. Then, of course, if it is strongly convex, it's easier to optimize. Then it's we have these two convergence rates depending on whether we have adaptive or fixed learning rate. But let's analyze them. So for convex or non-convex, because the if for fixed step size, do you remember? For fixed step size, yes. For fixed step size, we have this convergence rate. For a strongly convex, we have this. Okay. Now let's see. What do they do? Do you see this plus eta? Eta was the learning rate. Okay. Means that at the end, you tell me, limit t to infinity. It means that after infinite number of iterations, I'm supposed to reach the actual minimum, right? Do I reach there? What was this, by the way? The upper bound of my current f minus f star, right? How far? When t goes to infinity, this becomes eta, right? This also becomes eta. What does it mean? I never reach the minimum. I always oscillate around it by eta. And this is we have to accept it because we sacrificed the accuracy because we were lazy to calculate the full gradient, right? So that's approximation paid off here. So we did approximation to make our calculations easy in the stochastic gradient descent. But at the end, accuracy goes down. We oscillate around it. We never reach the actual solution. Did you understand? But let's go back to the convergence rate of gradient descent, which uses a full gradient. What was that? So it was order of 1 over t. Limit t to infinity, what happens? It becomes 0. It means that at the end, you will reach the minimum. Did you see the difference of full gradient descent and a stochastic gradient descent? In a stochastic gradient descent, we do approximation. We are lazy. We don't want to calculate the full gradient. It becomes easier for us, but at the end, we don't reach. We will oscillate it. By which amount? Exactly by the amount of a step size, eta. Right? Interesting. It's very interesting. Also, as you see, when it is strongly convex, it goes down to 0 much faster. So it's because it's an easier optimization problem. So advantage of SGD over gradient descent is that at every iteration, it's much faster, right, than every iteration of gradient descent because of less calculations and computations. This faster pacing of every iteration shows off more when n is huge. Can you tell me why? Of course, because when n is huge, the calculation of full gradient takes a lot of time, right? But when n is small, then you don't see the difference of spacing of stochastic gradient descent with respect to gradient descent, right? Also, can you tell me in a stochastic gradient descent, where in gradient descent, we had several termination criteria, convergence criteria. For example, we calculated the norm of gradient, right? We said that if it is small enough, stop it, stop the optimization. Here in a stochastic gradient descent, a puzzle happens. I don't have the full gradient. How do I find out when to stop? You can do several things. For example, you can only check the gradient, the L2 norm of one of the gradients, the one that you just sampled in this iteration. Although it's not that much accurate, but or you can take several gradients and calculate their mean, and then the L2 norm of the mean of the gradients, right? So again, for termination, you also are doing some kind of approximation. And we can also have line search with a stochastic gradient descent. And also we can have momentum. Okay. So we said that full gradient descent is good, but time consuming to calculate the full gradient at every iteration. Also, we had a stochastic gradient descent, which was very fast at every iteration, but it was not accurate much. So each of these has some flaw. Let's consider a middle case scenario, which has the best of the two worlds, right? A middle case scenario. A middle case scenario is what? Can you guess? So full gradient calculates all of the gradients, n gradients. A stochastic gradient descent only calculates one gradient. So the middle case scenario, let's calculate several gradients, right? At every iteration. It's called mini batch stochastic gradient descent, also called hybrid deterministic stochastic gradient method. So basically it means that let's break down our data into several chunks, and we call each chunk a mini batch, a batch or mini batch, right? With some batch size, right? Let the batch size be B, denoted by B, standing for batch, right? And I divide my data into batches in a way that the batches are usually, I do that. You can do it in various ways, but usually in the literature and also in the industry, they do this. They divide it into non-overlapping batches, right? So the union of the batches becomes the whole data, and not any two of those have any overlap. Okay. In other words, they are disjointed. And the batch size, how many batches will we have? If n is the number of data points in the data set, b is the batch size, the number of batches becomes n over b, but it might be a float number, so we round it down, right? Floor of n over b. Any questions so far? No? Okay. So we can also, rather than this, we can also sample points for a batch during optimization. So in two ways we can make the batches, right? either before starting the training of neural network, I have some data set, I divide it into several batches, right? Then while I'm training, I randomly take the batches one by one. So basically the libraries actually do that, because we will see that every time we go over all batches once, we call it one epoch. Okay, one epoch. Epoch, E-P-O-C-H. So basically, one epoch means that I have seen my data, my whole data once. Then I can go to the next epoch. Okay, and in every epoch, I'm getting all of the batches one by one, right? So I have a nested loop, one loop over the epochs, one loop inside over the batches. Okay, and usually at the start of every epoch, they shuffle the order of batches. If I don't shuffle, what happens? At every epoch, so in this epoch, I took the first batch. In the next epoch, at the start of next epoch, again, I use the first batch, and then the second batch, then the third batch. I don't want my neural network to be to learn the order of the batches. Is not important for me to be sensitive to the order, so I shuffle it. Okay, these parts are practical parts of neural network. It's not theoretical. Okay, so we shuffle the batches at the start of every epoch, and then we take them the shuffled batches one by one until we go over the whole batches. An epoch is completed, we go to the next epoch. Okay, or another way to do that is that we sample the batches during optimization, and this is less common. So the more common was that we divide the data into batches once before the start of training, then we shuffle them, right, at every. Or another way is that we sampled our batches during optimization. So as I said, epoch in mini batch stochastic gradient descent, when all of the batches of data are used for optimization once, an epoch is completed. After completion of an epoch, the next epoch is started, and epochs are repeated until convergence of optimization. Okay. In mini batch stochastic gradient descent, if the kth iteration of the optimization is using the k prime batch, okay, so consider the kth iteration, then consider the k prime batch that we have, then the update becomes this. This is exactly the gradient descent that the mini batch stochastic gradient descent. Because why? If the summation is over all of the points, it becomes a stochastic. It becomes gradient descent, full gradient descent. Here I'm just having the mean of gradients for the batch. For the batch, this is called mini batch scale. And also my learning rate can be adapted. Agreed? This 1/b sometimes is dropped, doesn't matter. If it is dropped, it is absorbed in the learning rate, right? Mini batch stochastic gradient descent is used significantly in machine learning, especially in neural networks. So what I'm saying is that not just for neural networks. You can use a stochastic gradient descent in statistical machine learning, right? Because of dividing data into batches, mini batch stochastic gradient descent can be solved on parallel servers as distributed optimization methods. So you can distribute that. You can also, in distributed optimization, we usually distribute our optimization and then we aggregate them again, then we distribute, then we aggregate them again, right? We see this behavior in federated learning also, right? So we have, I think you know better than me, right? In federated learning, we have one central server usually, and we have several servers. This is a part of machine learning. Then we say, let me briefly tell you about federated learning when working with neural networks. Assume I have a neural network. I have a copy of this neural network in several servers, and these servers don't see each other. Only they see the central server, right? Then I can say at every iteration, I ask these servers to calculate the gradients by backpropagation. Okay. Then they give their weights to me, to the central center. I aggregate them. This gives me the aggregated gradient, and then I give this updated weights back to them. So they update their weights by the aggregated gradient. Then they do the next iteration. Then they give. So this goes back and forth, as you see. I distribute the calculation, then I aggregate them. This main idea of distributing and then aggregating is used a lot in all of the distributed algorithms. And in this specific algorithm that I said, because we have various ways to do distributed algorithms. For example, we can have peer-to-peer distributed computations. So it means that we don't have any central server. So I only consider my neighbor server, and the servers only consider their neighbors. So there is no boss. Okay. This way to do it in a distributed way is good because it's not sensitive to attacks. If a hacker attacks this server, the other servers will not be affected. Maybe your neighbors only will be affected, right? But what if I have a central server? The hacker only needs to attack the central server. The whole system shuts down, right? These are related to privacy and security as well. So again, here we have calculation of gradient in various batches. Therefore, it gives us the opportunity to do it in parallel. That's why we can use GPU for neural networks, right? To make it parallel and faster. Agree?
Is the gradient has the same meaning as weight?
No. So the weights are the optimization variables in the neural network. The gradients are the derivative of error with respect to my optimization variables, which are the weights. Okay. Now let's talk about convergence rate of mini batch stochastic gradient descent. Okay. So consider a function which is decomposable, and it is bounded below, so it doesn't go to minus infinity. Each fi is differentiable. Okay. Let the domain of function f be d and the gradient be L smooth, and assume that the step size, the learning rate is fixed. Okay. The batch wise or mini batch gradient is an approximation of the full gradient, right? Of course, the bigger the batch, the more accurate it is, the approximation is. And the batch, assume ET is the error at the tth iteration, right? Then this, do you agree that what is this? This is the gradient in the mini batch stochastic gradient. What is this? The full gradient, which is if it is decomposable, it becomes 1 over n summation of all of the derivatives, right? Ideally, they must be equal, but they are not. It's approximation. So it's equal to this full gradient plus some error. And this is the error of approximation. Okay. Now, what is the convergence rate of mini batch stochastic gradient descent for non-convex and convex functions? It can be proved that it is equal to this equation 28. It's in the order of 1 over t plus squared L to norm of ET. Okay. Does it make sense? Let's analyze it. Does it make sense? Yes. Why? Let's increase the batch size. What happens? This approximation becomes more accurate, right? So the error ET goes down. Agree? When in the best case scenario, ET becomes 0 when the batch size is equal to the size of data, right? When ET is 0, this becomes O over 1t on the order of over 1t. 1 over t is exactly the convergence rate of full gradient descent. Do you remember? We just saw it in previous slides. So it makes sense. When the approximation is exact, the convergence rate becomes a convergence rate of full gradient descent, right? Also, it tells us some other thing. What does it say? I have some error ET. Again, at the end, limit T to infinity. At the end, I never reached that thing. I always jump with some step size of ET. And the better my approximation, the less the ET, the less jump I will have, the less oscillation I will have at the end around the solution. Agree? When it is strongly convex, mu strongly convex, then this is the convergence rate. Again, it has the same analysis. Okay. Now, as I said, we can have various ways to take the batches, right? Let's analyze it. Let's analyze it. If we sample the batches without replacement, that is sampling batches by simple random sampling before startup optimization, or with replacement, that is bootstrapping during optimization. So again, one way is that I divide my data into batches. It's like I'm sampling without replacement, right? I take one batch, I throw it away. Then I take another batch, I throw it away. So the batches become disjointed. But if I do it during optimization, the batches might have overlap. I take one batch, I put it back. Then in the next stretch, I take another batch, right? So basically, either I have simple random sampling without replacement, with replacement, without replacement, or with replacement. According to proposition 3 in reference 11, I think reference 11 is one of my tutorials on sampling. Its title is Sampling Algorithms from Survey Sampling to Monte Carlo Methods, Tutorial and Literature Review. That's about sampling, okay? So it can be proved that these errors are either equation 30 or 31. Equation 30 is for sampling without replacement. Equation 31 is for sampling with replacement. The formula is not important. The analysis is important. Let's analyze it. What does it mean? By the way, what is sigma squared? Sigma squared is the variance of the whole data set. Okay? Now, sorry. Yes, sometimes it gets tired. This. Okay. We will have breaks soon. Just let me cover this. Guys, let's analyze these two equations. What do they mean? So in equation 30 was for disjointed batches, right? Then when does this become 0? Because this is the expectation of the error, squared L2 norm of error, right? I want it to become 0. The ideal case is 0. When does this become 0? Set this equation to 0. What happens? When B over N is 1, right? When B over N is 1, what does it mean? B equals N. And that's exactly what it means. So it means that my batch size is the whole data. It means that my one batch becomes the whole data. And it becomes exactly the full gradient distance, right? The error becomes 0. What about the next thing? Wait, in the next way, when does this become 0? When B goes to infinity. Why? Because my batches are not necessarily disjointed. For me to cover the whole data, I need to let B increase B until it becomes infinite. I don't know if you got it or not. So basically, because assume I have my whole data, right? Then I might take this. Then I might take this. Then I might take this or this. But if I increase B to be infinite, then I will definitely, when I'm doing it randomly, I definitely would take the whole thing, right? This is the reason. This is the reason.
The start optimization. So here the optimization refers to 23.
Which one? I didn't get it.
So like without replacement, we do something before the start of optimization. So
during optimization, I mean during training of neural network, I can at every iteration. So I have iteration over the epochs. I also have iterations over the batches, right? Then I can also take the batches randomly from data. Then this becomes equivalent to sampling with replacement, because I take one batch, I do my calculation, and then I take another random batch, and these batches might have overlap. But if I do it before start of optimization, then they are disjointed. So, and now I'm just analyzing them. For when they are disjointed, it becomes equal to the full gradient descent if my batch size is a whole data. But if I'm doing it randomly, and I'm like blind, I'm taking randomly, they might be disjointed, might not be disjointed, might be disjointed, right? So the batches might have overlap. If I increase B to be infinite, by one blind random taking, I will take the whole data.
Right? One is for
yes.
So here's the optimization. Which loop are we talking about?
So at the start of epoch, I mean. So without before optimization, I mean before the epochs, I break down into the I break down data into batches. But with replacement, I mean at the start of each epoch, I take the batches randomly. Okay. So let's have a break. After the break, we'll go over adaptive learning rates, and we will cover ADAM. ADAM is another. So nowadays, backpropagation is used with two main approaches: either a stochastic gradient descent, which we covered, or ADAM. In the libraries, these two are most common, right? We will cover it after the break. So let's come back at 22, right? 22 to 9. So 15 minutes of the break. 23, 22 to. Thank you. Okay, yeah. So now we go to adaptive learning rates, meaning that let's update the learning rates adapted during the optimization. We can adapt the learning rate in the stochastic gradient methods. Three most well-known methods for adapting the learning rate are AdaGrad, RMSProp, and ADAM. Okay, we're gonna cover them, and they are related to each other. So adaptive gradient is also called AdaGrad method. It was proposed in 2011. Okay, it updates the solution iteratively in this way. So how is it different from gradient stochastic gradient descent? Stochastic gradient descent doesn't have this G inverse here, right? So here we have G inverse before the gradient of Fx gradient of Fi at point X, right? And what is this G? This G is a D by D diagonal matrix, okay? And D here is the dimensionality of X, right? Dimension. Whose jth element, the element on the diagonal, is equation 33. So what is that? Here, epsilon, why do I have that? It's a small positive number. Why do I have that? Because I have G inverse, right? I want it not to be singular. Yeah, to become full rank, not to be singular. Therefore, I'm adding a small positive number to the main diagonal, right? To become full rank. So for stability, or for making G full rank. What is I tau here? Is some randomly sampled point from 1 to n at iteration tau. Okay, so randomly I'm sampling some point. And what is this? This is the partial derivative of f I tau with respect to the jth element. So basically it means that because I have n gradients, do you remember? This is a stochastic gradient. This is, I have gradient of f1 until gradient of fn. Here I take one of them randomly at this iteration, and also this basically means this. Do you agree that gradient of fi is a vector? Do you agree? Because the error is a scalar. My x is a vector. Derivative of a scalar with respect to a vector becomes a vector. So gradient is a vector. Delta j means the jth dimension of that vector. Okay. And so basically, if we put this inside this equation, I will have equation 34. Okay, I will have equation 34. And let's analyze it. What does it do? What does this do? So AdaGrad keeps a history of the sample points. As you see, I'm summing from all iterations from scratch until now. Okay. So first off, it has a history. And it takes derivative for them to use. Okay. So here I'm taking derivative. During the iterations so far, it means this so far, right? If a dimension has changed significantly, it dampens the learning rate. Why? What is the definition of derivative? It means how much I have changed, right? So what does this mean? The jth dimension, the jth direction, how much does it has it have impact or changed, right? If it has had a lot of impact or change, dampen the learning rate for that. Otherwise, don't decrease the learning rate. So see, do you see that? Hence, it gives more weight for changing the dimensions which have not changed noticeably. Basically, it says that it's a democracy. It says that let's give a chance to everyone, right? So if a direction is being noticed a lot and a lot, this time don't notice this. Ignore it, dampen it. Give more notice to others too. Give them a chance, right? Did you understand? This is basically what it is doing. Okay. In this way, all dimensions will have a fair chance to change. Not just one direction, right? In humans' life, don't only put all of your eggs in one basket. Experience every different, expand your experiences, right? Okay. So that was the AdaGrad over, right? Okay. Now the next thing is RMSProp, short for root mean square propagation. It was first proposed in 2012. Okay, in reference 30. And it was unpublished. Why? It was proposed by Hinton in his lectures in University of Toronto when he was teaching. He never published that. It is in one of the slides of Hinton. Okay, so it is an improved version of RProp, resilient backpropagation, which was proposed in 1992. It is an improved version of that, which uses the sign of gradient in optimization. RProp uses the sign of gradient. This also uses the sign of gradient. So inspired by momentum, do you remember this was momentum? Do you remember? You saw it in previous session. It updates a scalar variable v in this way. As you see, there is a close similarity to what we have in momentum. Okay. And here I have a linear combination between my previous v, okay, and my squared autonormal of norm at this iteration. Okay. By the way, v is some scalar, which is defined in this algorithm. Okay. And it is updated iteratively. And how do I update it? By a linear combination of my previous v and my gradient, similar to what we had in the ideal momentum, right? Gamma is between 0 and 1. As you see, it's a linear combination between V and squared L2 normal gradients. For example, gamma can be 0.9. Then it uses this V that it is updating iteratively to weight the learning rate, right? So as you see, this is how it is a stochastic gradient descent with RMSProp. And as you see here, if you drop this part, it becomes a stochastic gradient descent, right? The difference is this denominator, square root of epsilon plus V. And epsilon is for stability, not to have division by 0, right? If V is too small, then it becomes division by 0. So compare this equation 36 and equation 34. Very similar. Do you see that, the difference? Very similar form. So I have square root of epsilon plus something, but here is summation of gradients at the directions J, right? Squared. Here I have V, where V is updated in this way. Okay. Here I haven't explained RProp. If you go and see the RProp, it uses a sign of the gradient. So basically, if it is a scalar, I think sign is obvious. But when it becomes a vector, gradient sign in scalar means positive or negative, right? When it is vector, I haven't read RProp in depth, but if either it is element-wise or it's direction of gradients. I need to read that carefully to see what it means. But I know that it uses a sign of gradient. And this RMSProp is an improved version of RProp, okay, which wasn't never published. Why is it important? You might say, why is RMSProp important? Because it yielded to Adam. Adam is all of these three things that I'm talking about are related to each other. And at the end, they ended up with Adam, which is very good. Okay. Adam is short for adaptive moment estimation. So Adam is short for adaptive moment estimation. It's not related to Adam and Eve. Okay. So adaptive moment estimation optimizer. What does it do? It improves the RMSProp. RMSProp, which was proposed by Hinton in his lectures, right? By adding a momentum term. Okay, so it updates the scalar V that we had in RMSProp and the vector M. Now this time it also has it introduces a vector. This is the vector M, d-dimensional vector M, where M is updated in this way, a linear combination of previous M and the gradient itself. The gradient is a vector, right? Therefore, M is also a vector. V is a linear combination of previous V and a squared L2 norm of V, as we had in RMSProp. And we know that a squared L2 norm of gradient is a scalar, therefore V is also a scalar, right? So now, the gamma 1 and gamma 2 are between 0 and 1 to have linear combination of this, right? Then we normalize these variables. We normalize them, right? So M hat is 1 over 1 minus gamma 1 M. V hat is 1 over 1 minus gamma 2 V. Okay? With the same gammas that we had, we normalize them. Okay? Then it uses these to update. As you see here, I don't have the gradients anymore. I have M hat. But M hat is related to the gradient in this way. M hat is a linear combination of the gradient, which we use in a stochastic gradient descent, and the previous M. As you see, it's using the log of a history. The idea of momentum here is hence we name this momentum, right? Momentum term. So all of these, did you understand that they're kind of using the history? all of these three algorithms that I just talked about, they're using the history. They have the backbone idea of momentum for adapting the learning rate. Did you get it? Did you get it? So the Adam optimizer is one of the mostly used optimizers in neural network. Was it hard? No, but this is one of the most famous ways to optimize neural networks. And this is not replacing backpropagation. Backpropagation, you know that is, I said it is gradient descent and chain rule, right? Now it becomes a stochastic gradient descent with Adam learning rate and chain rule. Or it becomes a stochastic gradient descent with simple learning rate and chain, right? Did you get it? So Adam is just for adapting learning rate.
Say adding a momentum term, is that equals to we are trying to learn from the history of the data?
Yes, exactly. This is because always my momentum is a linear combination of my previous momentum and my current gradient. Therefore, it's using the history, right? And what did the momentum do? It dampens the oscillation, right? So it helps us not to have too much oscillation as well. Agree? Because it has momentum in it too. Did you get it? Help us not to have too much oscillation. Do you remember? I talked about it, I guess. So let me recall momentum. X of next iteration was X of previous iteration minus delta X, right? This is the general thing. When we were not using momentum, delta Kx, sorry, plus 1 was eta. So this is, if it is plus, this is minus eta gradient of f. Do you remember? This is a gradient descent, right? But when we were using momentum, it was minus eta gradient of f plus alpha previous delta x, right? Do you remember this? This was momentum term. Why does this dampen the oscillation? I can say it in two ways, in English and in math. In English, I think it's obvious because I'm using the history. I shouldn't deviate from my history much. So if I was going in this way, I shouldn't go too much like that. It deviates from my history a lot. I go like this. Now in mathematics, let's see why. So this was my previous update. Currently, I'm here. Assume my minus eta gradient of f is here, going in this direction, right? What is my previous update? It was this, right? But starting from where I am, right? This vector becomes like this, right? Agreed? What is the linear combination of these two vectors? So I pulled where I was going a bit toward where I am. So it became a smoother. So in general, it becomes like this while it was like this. I was oscillating a lot, but I pulled it not to go too much oscillation, not to have too much oscillation. So mathematically, we saw that. In English as well, it makes sense in human language, right? We're saying that, yeah, I'm using the history. I shouldn't deviate much. Oscillation, fluctuation. Okay, now coding neural network. Let me, I believe I had it here. Just give me a second. Sorry about that. Yes. Okay, just give me a second, please. So this is what. Now let's see the code of neural network. Guys, please don't talk because we will not be able to focus. So now let's go to practice, right? So simple linear and nonlinear regression using feed-forward neural network. First off, we need to import our here. By the way, I'm coding in Jupyter notebook, right? So there are two ways to code Python in either in .py files. Then you need IDEs like VS Code, right, or PyCharm to run them. Guys, please don't talk. I can't concentrate. Please. So either we use the IDEs or we use notebook. Notebook will be block by block. Okay, we run the blocks. I don't know if you have coded in MATLAB or not, but if you're familiar with MATLAB, notebook is like command line of MATLAB. .py is like the M file. Okay, that's for those of you who know MATLAB. Okay. Anyways, now we need to install our packages, right? In Python, there are two ways to install packages, either pip or conda, usually. So usually in academia, people use conda, or short for anaconda. So conda has some packages that you can install. And whenever you work with anaconda or conda, you usually tend to install packages by conda. So you have conda environment. You make a conda in each environment. In each environment you can install your packages. Okay. Then you install your packages in your conda environment. Usually you tend to install packages by conda. If it doesn't work, sometimes it has conflict or you don't find the correct version, then people go to pip. Then they install that package by pip, right? But in industry, especially in industry where they are using Unix or Linux systems, they usually work with pip. In industry where people work in Windows, they usually work with conda. Again, these are the tastes of the people in different companies. So then, as I said, you need to install this. For example, I want to install Torch. So there are several libraries for coding neural network. The two important ones are PyTorch and TensorFlow. Okay. There is another one which is Keras. Keras has been combined with TensorFlow. So you can see TensorFlow and Keras as one thing. And also, so there TensorFlow, Keras, Keras, and TensorFlow is like this, and PyTorch. PyTorch, I believe, TensorFlow is for Google. Okay. As far as I remember, PyTorch, it was initially proposed by Facebook, I think, if I'm not wrong. Okay, so that is why, and we know that until several years ago, Facebook was leading natural language processing, and Google was leading image processing. That's why, at least until several years ago, whenever you saw GitHub, the codes for image processing and computer vision were usually in TensorFlow, written in TensorFlow. The codes for natural language processing were usually written in PyTorch. Nowadays, it has been combined in a way that I think PyTorch is winning because PyTorch is easier to work with. TensorFlow is really a pain in the neck because it updates itself. Sometimes it is incompatible with the previous versions, and it's a headache really. But but you can work with both, doesn't matter. And PyTorch is usually, if you know what is NumPy array, so the tensors are more like NumPy arrays. So if you're more comfortable with NumPy arrays, maybe you will be more comfortable with PyTorch as well. Okay, that's one thing. So now when we want to install the PyTorch, the library for PyTorch is called Torch. Okay. So we install it by, for example, pip. Then we should say pip install Torch, right? But here I'm using Google Colab. So by the way, notebook, you can run it in various ways. one of them is Jupyter Notebook. In this way, you run it on your own computer, your local host, right? But if you want, you can use the online tools for that, for running the notebooks. One of them is Google Colab. The other one is Kaggle, right? They have these things that you can run on. And they have CPU, GPU, you can choose. I want to use GPU or even TPU. These are the things that you can use. So here I'm using Google Colab, for example. In Google Colab, you need to use this notation as well. What is this notation called in English? What? Exclamation mark before pip. Okay. So then Shift Enter runs the code, the cell. Let me run it. So now it's running and it is installing the thing. Requirements already satisfied. I think already had installed many of these. Okay, it's installed and it has a green tick. It means that it is run without any error. Now we import the packages or libraries. So import is like include in C, right? So import torch, then import torch.nn is short for neural network as nn, right? Then from torch utils, usually the packages have utils. Utils, are the things that you can use for your package, right? And whenever you write a code, also code it in a modular way, and you put the useful functions that you are going to use across different modules, put them in the utils folder of your code. So we have torch.utils, or it's, I think, short for utility. Utils.data. So it means that these are utils for my data loading, data pre-processing, and this. From that, import data loader and data set. By the way, what do these dots mean? They mean two things in Python. Yeah, so for example, torch.utils.data, there are two meanings. They have two meanings in Python. Either it means that you have, for example, assume you have torch.nn. It might mean that, usually it means that you have a torch.py file. Inside that, you might have a class or a function nn, okay? So when you have a file, inside that you have a function or a class, then you say the name of that file dot the name of that class or function. But usually classes are camel case, so they start with a big letter. And functions are a small case, okay? Another meaning for dot is the folders. So you might have, for example, a folder torch. Inside that, you have a folder, a subfolder or subdirectory. Utils, inside that you have data.py, for example. So dot has two meanings in Python. Did you get it? Either nested folders or some function inside the file. Then here I'm saying that from that file, import these things. You can also rename them if you don't like their names, but usually we don't rename the important things. Here, import data loader, I can say import data loader as Benjamin. Then I use the word Benjamin as data loader, okay? The data loader and data set. Usually we import, so matplotlib.pyplot is for plotting in Python. We usually should make it long, right? We make it short as PLT. We also import NumPy. NumPy is for working with vectors and matrices. As NP, short for NumPy. And what is from Taqaddum or TQDM? Import Taqaddum. Taqaddum is an Arabic word. So because most of the developers of TQDM package were Arabs. And Taqaddum means progress in English. So it shows a progress bar. Okay, that's the reason. So so let's run this cell. So we are important. If any package was not installed, it would throw an error. Then we define the network. So here we determine our device. Device is torch, so we can say torch.device and say whether it's CPU or GPU. Here we are saying that use the first CUDA is it means that so CUDA is actually one of the, I think, languages for working with GPU. CUDA that column 0 means that the first GPU, use the first GPU. If Torch CUDA is available, if I have GPU in my system, my PC, otherwise else use CPU. Okay, so I determine my device, which device I want to use. Of course, I prefer GPU if available. Hence, I have written in this way. Okay, so I run it. Then we go to this. Let me zoom further. We have a class. What is class? Do you know object-oriented programming? No. Yeah, all of you guys know that. Just briefly, I tell you that object-oriented programming, for this to explain very well, I think you should see the analogy of object-oriented programming and Plato's theory of forms in ancient philosophy. Do you know the analogy? All of you know. So what does Plato say in his epistemology and in his understanding of the world? He says that everything in this world has a true image, truth, essence in some world. Okay, for example, we have various roosters, right? We have a one true rooster without any color, because color itself has a true color, right? We have a true rooster without any characteristic, which is not about rooster in some world, logical world. Okay, that's the world of forms, or the world of ideas, right? So everything has some idea or form there, because idea is a Greek word, right? And for example, we are humans, right? But there is a true human there, right? So the difference with here is the desk. There is a true desk there, right? Without any shape, because we have rectangular shape, we have round rectangular desk, we have round desk, but the desk itself without any shape is there. So this is the philosophy of Plato. And now see the analogy here. The classes are like forms, right? For example, I can make a class of human, right? Then I instantiate from that class to make objects of that class human. Then I name it Benjamin, for example. Then I name it Jennifer, Jack, whatever, right? So I now when I instantiate the object of that class has some functions to do. For example, in this case, walking, talking, these are functions of human, right? These functions are called methods in object-oriented programming, especially in Java. Okay. And one of the functions is used immediately when you instantiate that object. So when you instantiate that object, one of the functions is immediately called, and that's called the constructor method. Okay. What does it do? Because every class, every object of the class has some attributes. Every class has some attributes. For example, human has the attribute of skin color or height, width, whatever, right? These things. Weight. Whenever you make an object, you can specify the values for those attributes, right? Did you get it? So we do that. And so we have some attributes, and also we refer to the object itself by self. We say self dot that attribute, right? Self dot that attribute means that attribute, specific attribute for me, for Benjamin. If I say self dot some method such as walk, it means that Benjamin, you walk, okay? Also, the classes can inherit from each other. For example, I have a class of human, it inherits from the class of mammals, right? And the class of mammals inherits from the class of animals, something like that. So when you inherit from some class, you will get its methods and its attributes, but you can have additional methods and attributes. Okay. I think by analogy of theory of forms, you can understand object-oriented programming very well. So now here I have a class of neural network from Torch, PyTorch. Sorry, I define neural network. I define it. This is what I name. You can call it Benjamin, right? Class that, and this is camel case, right? Camel case, and it inherits from this class nn.module, which is in Torch, right? Okay, it inherits from it. Then this is my constructor method. So what do? I say initialize, run the constructor of the NN module, then define the layers, layer 1, layer 2, layer 3, layer 4. So here I'm gonna have fully connected neural network, 4 layers. So what does this mean? One layer, it takes 1 neuron, then it goes to 10 neurons, then from 10 neurons to 20 neurons, from 20 neurons to 10 neurons, then from 10 neurons to 1 neuron. Okay. Then I also define the ReLU activation functions, ReLU 1, ReLU 2, ReLU 3. Right? Then I have a forward method in the NN module. I'm overriding that. Okay. So I'm saying that for me, run the forward in this way. Okay. So what does it do? It says take X as input, right? Then feed it to the layer 1. Then feed it to the ReLU 1, then gets X. What is this X here? At the end of the layer 1, after the layer 1. Then feed this X to layer 2. Then to ReLU 2, it gives you the X after layer 2, right? Do it for the 3rd layer as well. Then the 4th layer, I don't have any activation function. Why? Because I want to do regression without any bound. Okay, without any bound. Did you get it? So let's run it. Okay, I ran it. Okay. Now I have it in my memory, I can use it. So now instantiate the neural network that I just defined. The object name is usually a small case, right? And then we can print it. As you see, it tells me these are the layers, these are the features, input features, output features, right? Now the optimizer. We can either use a stochastic SGD, a stochastic gradient descent optimizer, which we just saw, or Adam optimizer, right? Which you just saw here, torch.optim, short for optimization, .sgd or torch.optim.adam. You can also specify the initial learning rate, right? So, and also it takes the net, which we just defined, we instantiated that. Net.parameters, the weights of the neural network, it takes them. And also I'm defining the loss function. Here I'm using torch.nn.mean squared error loss, right? Let's run it. Now data loader. So far we defined the network, right? Now the data loader. We need to load the data set. So do you remember? We imported data set from Torch utils. So I'm defining a class data. You can call it anything. It inherits from dataset, right? Then its constructor is this. I say I get X and Y as input, right? And X is your data, Y is my label, right? So self.data, again, these are my names. You can name it anything. Equals torch from NumPy, X.reshape. So let me tell you the details. Here I get X, I reshape it. What do I mean by -1, 1? Reshape it to become a column vector, right? So it means that 1 column and any number of rows. So you can calculate yourself the number of rows, right? When you reshape your vector, your matrix, whatever, to become a column vector, it can calculate automatically how many rows it needs, right? -1 means torch, you calculate it. Okay. Then I say from NumPy. So this here is a NumPy array. I convert it to a torch tensor, right? Torch.NumPy array. Then I say cast it to be float. I don't want it to be integer or anything, right? Cast it to be float. Then what is len and get item? These are 2 methods in this class data set that I'm overriding. What do I mean? Whenever I have output of this class, the user uses len, which is the length, right? Then I say return the length of my data. So here I'm saying that don't consider my label. return the length of my data, right? I can define it. What about get item? It means that whenever your user says, for example, data in brackets 0, what does it mean? What should I do? I tell you, hey, data loader, you should do this. You should say get, so you get item, right? Self data item, the data point, self label item, the label point, and then return both data point and label point as a tuple. Okay. So let's run it. And now, so now I'm defining a function this time. Defining a function load dataset. What does it do? It takes X train and Y train, X test and Y test, right? Data and labels of train and test. Batch size, I determine it to be 16. Then I said data here. I'm instantiated the class data. That's what I defined, which itself inherits from dataset, the dataset, right? So here I instantiate that for X train. It gives me train DS. DS short for data structure, right? Then also, so now my data loader, which also imported from Torch, gets this object as input. Okay, train DS. With the which batch size? The batch size 16. I'll also say for train, I want it to be shuffled, shuffle it, right? So it gives me the train loader. I'm gonna use that for loading data. I do the same for test, but for the test, I usually set the shuffle to false because the order, I don't change the order of the test data, right? Then it returns the train loader and test loader together. Now I make some toy dataset. So dataset type, we can have linear dataset or non-linear dataset. If you run this, although this is a non-linear function, but in the range that I'm considering, it's almost linear, Otherwise, it's non-linear. And then I can plot it. Let me plot it. So for non-linear, for linear data, so as you see, it's almost linear for train and test, okay? And then we can train the neural network. What am I doing here? So I call the function load dataset that I had, right? It gives me the train and test data loaders. Then the number of epochs, I say 1000, okay? Then what do I do so I have, as I said, we have nested loop. One for loop over the epochs, okay? What does this do? Let me zoom further. For epoch, so in range n epochs, it means that goes from 0 to n epochs minus 1, okay? But I use taqaddum to have the progress bar, like as you see here. And also I say the description, the taqaddum should be epochs, so it writes epochs here. Then I also can store the loss function, the loss values at the iterations in a list, right? At every epoch, I reset that list. Then here is my nested loop. So I have a for loop over the batches inside the epoch. Train loader. What happened? Train loader, right? Because I need to use train loader. I'm training right now. It gives me, when I do that, it gives me data batch and label batch because we defined there, you remember? It gives me X and Y. And I use enumerate. Enumerate also returns a step size, the step, which step of the iteration you are in. Then you say data batch, you got the data batch, then bring it to the device that you defined, whether it was CPU or GPU, right? Then it gives you your data batch and label batch after the device. Then feed this to your neural network, right? It gives you some prediction. Why? Can you tell me why? Let's go back to our net. Where was our net? When you run that net x, prediction of always net x, all equals net x, it runs this forward. So it gives brings puts x inside the forward function, at the end it returns x, which is the predicted value, right? The output of the neural network. So it does that. Let's go back to where we were. Yes, so here we have this prediction, and then I give the prediction and the actual labels to the loss function. It gives me some loss, right? Then I want to store it in a list, the loss values. So you can't do it. Why? Because this loss might be in GPU. You need to bring it to CPU. Whenever something is in GPU, you can't store it in as a list or NumPy array. You need to bring it to CPU. So I bring it to CPU, then I detach it. Detach is also detach that from the GPU to CPU. And then dot item, if it is only one thing, it gets that item gets that one thing from that. Then you append that to your list that you have. Then you say optimizer.0grad. You need to make the gradient 0 every time, otherwise it's wrong. It is one of the things that you need to do in practice for PyTorch. Okay, at every iteration you need to make the gradient 0 after you're calculating the gradient. So otherwise the gradients will be accumulated, and that's wrong, right? Then you do so you 0grad the previous optimizer, the previous iteration. Then you do the backward and optimizer dot step. These two lines is a backpropagation. One update of backpropagation that we just talked about. Do you remember? So today we both covered theory and practice. Then we append that. So here I'm taking the mean of these losses, np.mean, right? Then let's run this, and you'll see the progress bar as well. See? And progress bar, as you see here, it shows how much time has passed and how much time is left. So it can estimate based on the pacing of your iterations how much time is left. And it's very useful in industry. For example, you run it, your manager says, when will it be ready? You see the progress bar and say probably tomorrow at 2 p.m., right? So you can see that. And then testing. So here you have prediction list for Torch. Okay, when you are doing the test, you should use with Torch no grad. So you should do all of your tests inside this. Why? Because I don't want to calculate gradient anymore in the testing phase. And then you have a for loop again on the test loader this time. All right, which is not shuffled because we set shuffle false. Then we feed that data batch of the test to the network. It gives me prediction, and then I'll store them in a list, right? So these are the predicted labels. Then visualize it. Sometimes when I run it, it doesn't work. If it doesn't work well, so it works well. It works well. I'm happy about it. So as you see, we have test data, and our prediction almost follows our test data. See, I'm not sure whether it works for our nonlinear data too. Let's try it. So let me change my linear to nonlinear. So this is nonlinear data, right? Train and test. I need to run this again, train this again.
What's the advantage of using notebook compared with PyTorch?
Okay, what is the advantage? So each of these has advantages. What is the advantage of .py and the notebook over each other? So the notebook is for trial and error, because you can have blocks and you run the block and you forget it, and then you go to the next block and you do. So it's for trial and error. Usually codes in notebook become very dirty, very dirty. And also it is prone to having errors. Why? Because you might change the order of your operations. So for example, you run this block, then you go and run another block at the end, then you come and run some block in the middle. Then the order of memory has changed. You should be careful about the order of running the blocks, right? So it is very sensitive to the order. But .py is cleaner, is good for projects. And when you want to give your project as a final project to your manager, you should give it as a .py, I believe, unless you want to report the intermediate steps. Another good thing about Notebook is that you can print the results and the plots in between the codes. But in .py, you need to generate the plots and save them somewhere. Okay. So where were we? So I trained these. Now in the test phase. No, it didn't work. Sorry. For nonlinear, it didn't work. I don't know why. I think it might be because of saturation of gradient or something. But this code used to work a year ago. Okay. But anyway, but the general things that you should do is this, right? Did you get it? Did you get? So I was trying to tell you the steps of what you should do in practice in Python. Okay. So let's go back to the next topic. Any question about the code? No? Yes. Yeah. No. So when we were inheriting the class, where was that? What? Yeah, it was here, right? Here. Here, you mean. Okay. So when we were inheriting the class, what do we mean? So that class has a method forward, also has some attributes like nn.linear. I think you get it from somewhere else. But for example, forward is from nn.module. So where does nn.linear come from? It comes from this import that you had. Torch, import torch nn as nn. So you get the nn.linear and the ReLU and these things from that. However, you need to have the constructor and forward implemented for your network. So basically, so in Python, especially when you are doing team working, you have abstract classes. Have you heard of that? So this is also in the abstract classes. Its package is ABC, short for abstract classes. So what does it do? It's very good. So you can have, when you have an abstract function, it means that you put it, and usually they put it as empty function, just for the sake of template. And people, when they inherit that class, they will implement that function or that method. You might be wondering, when it is empty, how is it template? It is template. Why? First off, its name, the name of the function. Secondly, the inputs, the number of inputs and the name of the inputs. Thirdly, the output. So your manager, your team lead in your industry can say, I can make a class with all empty methods. It's called abstract class with all abstract functions or methods, and then it divides you into several teams and says, all of you inherit from this class that I determined and implement your own functions, but with the template that I gave you. Okay, assume here and that module is a template. It has some forward, and I need to implement the forward. Did you get it?
Any limitation for using the Google Colab GPU?
So when you use GPU, it becomes faster.
Yeah, I mean, is there any limitation?
Yeah, there is a limitation. It doesn't let you use everything. But usually, for example, if it is too much occupied by too many people, it might not let you use GPU. Also, there is a limit over on the time, how much time you use that.
Is it free?
The Google Colab is free. Yeah. Kaggle is also free, but they have time limits. Any other question? No. Okay, so let's go to the next topic, which is CNN. Okay. Convolutional neural networks. So we have two slide decks for convolutional neural networks. One of them first talks about CNN and its fundamentals. The next one will talk about important CNN networks, such as ResNet. Okay, and this. First, fundamentals of CNN. Okay. Consider an image with its pixels as the data, right? So we have image, and the pixels of the image can be the features of the data, right? Then if the neural network is fully connected, what happens? Can it get the 2D image with rows and columns? Can it get? When it is fully connected, the input layer of the fully connected layer is just takes vector, right? Takes a vector. Therefore, obviously, I need to reshape my image to become a vector. Do you understand? Okay. But what it makes a problem without looking at this slide? Can you tell me what is the problem of reshaping an image to become a vector and feeding that to a fully connected network? Assume I have an image of my face. I reshape it to become a vector and I feed it to the fully connected neural network. A problem happens. What is the problem? Do I lose some information? Do I? I'm asking yes or yes. What kind of information am I losing?
Spatial coordinates.
Exactly. The spatial correlations between the adjacent pixels. Some spatiality, some neighborhoods are preserved yet, but some of them are destroyed. What do I mean? Consider these pixels 1, 2, 3, 4, 5, 6, like this, right? If I reshape it, for example, I reshape it in this way. Assume 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, consider the pixel 1. Its neighbors were 2 and 4. Of course, here 2 is still the neighbor of 1, but 4 is fall apart this time, right? Now, if we have two big image, the distance of 4 and 1 will be huge. Agree? So the spatial 2D correlation of the pixels has been ruined by this reshaping. Agree? That's why people thought of, why do we reshape the data? Let's change the structure of neural network. And they call it convolutional neural networks, which accepts, it can accept matrix or tensor. So you might have image, or you might have image with several channels, so it becomes like a cube, right? So it accepts a tensor in general without reshaping it. So in order not to have loss of information in our data, CNN is a neural network which uses convolution in place of general matrix multiplication. Do you remember we had general matrix multiplication? Recall that session that we talked about fully connected. It was U1, U2, X, right? What was Y? Predicted Y hat. So first off, we had U1 transpose X as a linear projection onto the layer U1. Then we fed it to the activation function sigma 1. Then we had U2 transpose. Then if we, at the end, we have any activation function, it becomes sigma 2, right? As you see, we have matrix multiplications here, right? Rather than this general matrix multiplication, if we use convolution in at least one of the layers, then we call it convolutional neural network. So in a convolutional neural network, we might have only one layer as convolutional layer, and the rest might be still fully connected layers as simple matrix multiplication. We still call that convolutional neural network, right? A CNN might or might not have one or several fully connected layers in addition to the convolutional layer or layers, right? Okay, CNN, did you know that it was initially proposed by Kunihiko Fukushima from Japan in 1980? That network was named neocognition in that paper. They named it neocognition. Then the idea of CNN was adopted and slightly modified for the task of handwritten digit recognition. This is exactly the paper which proposes MNIST dataset, right? The famous, what is MNIST dataset? It's a dataset of digits, handwritten digits, 0 until 9. At that time, it's 1989, Jan LeCun, who is famous now, very, he's one of the godfathers of AI nowadays, okay? So Jan LeCun at that time, he was funding for the project of handwritten digit recognition. His funding was that in the university. He was in the University of New York. Also, he's one of the heads of AI in Facebook or Meta. So at that time, he had this project, and they adopted the idea of CNN from Japan to use it on the handwritten digit recognition for that project, right? Then they worked on a paper which is now a very important paper, right? That was one of the main papers of CNN. So initially they proposed a smaller paper reference to. Later in 1998, Jan LeCun, in collaboration with Yoshua Bengio, who is another godfather of AI, they proposed the paper named LeNet, reference 3, which is very important, right? So Jan LeCun, Yoshua Bengio, all of these have become famous because of these very important works. Who is Yoshua Bengio? He's in University de Montreal. He's the godfather of AI in the whole Quebec, okay? And also the whole Canada. So they named it LeNet. Why? Because the main author, the main person in that project was LeCun. He named it LeNet. Lee is the start of the name of LeCun, Jan LeCun, right? And LeNet, net is for network, after the name LeCun. The paper 3, which I said very important in 1998, was the paper which proposed the modified NIST or MNIST. Did you know that MNIST is short for modified NIST? Yeah, NIST was a digits data set. They modified it and they called it modified NIST, MNIST, okay? Which is a handwritten digit data set, widely used as a benchmark in machine learning nowadays. Nowadays, whenever they want to cite the MNIST paper, they usually cite that MNIST. It's that paper that LeCun wrote, right? That's why it has a lot of citation, okay? So the structure of LeNet is shown in this figure. Take a look at this. So it takes the input, it doesn't reshape it. Some input, for example, 32 by 32, okay? 32 rows and 32 columns. Then it has some convolutions. It gives me several feature maps. What do I mean? We will talk about it in more detail. So basically, I have several kernels. Have you passed any image processing course? No? Yeah. So basically, when you want to do filtering on your image, what do? You have some filter, and that filter is usually small. For example, 3 by 3, 4 by 4, right? Then you slide it over your image, and we will see that in more detail, but I'm just saying that in English right now. We multiply the elements of that filter onto the pixels, then we sum them up, we take the average, for example. Then we replace that pixel with the calculation that I just did. Then it means that I have applied this filter on this image. Then based on the filter that I decide, it does something for me. For example, it detects the edges, okay? Or it detects the corners, or it smoothens the edges. So it does something for me, okay? And this filter is also, that I said is usually small, is also called the filter kernel, which is not related to the kernel in machine learning, like kernel SVM. They are different. It's filter kernel, okay? Now we have, in convolutional neural network here, for example, we have a bunch of kernels at every layer, not just one kernel. A bunch of filter kernels. I apply these kernels onto the image, and it gives me some output image. Do you agree? So I will have a bunch of them. So I have several feature maps. Then I do subsampling. I downsample it somehow. Here nowadays we call it pooling. We use pooling. I will talk more the details of this later. Then we use pooling to downsample our image to become a smaller image. Sorry about my voice. When I talk too much, this happens. Okay. So I have downsampled the images to become smaller. Then I do, again, a bunch of convolutions. Of course, the number of channels will increase here, right? Because I had several channels and I applied several channels on them again. So I'll have much more. Then I downsample again. At the end, usually, this was the idea of Likun, Benju et al., that let's have some fully connected layers at the end. This idea has remained until now. Nowadays, usually whenever you have a convolutional neural network, at the end, they put some fully connected layers. This idea has remained since then. Okay. Then at the end, we have some loss function. So they had some other things such as Gaussian connections, which are not used nowadays. Okay. So this structure is now one of the main dominant structures in simple convolutional neural networks. Whenever we say regular or simple convolutional neural network, you usually mean this, something like this. So we have several stages in a convolutional layer. So consider one of the convolutional layers. Oh, by the way, I forgot to say one thing. Do you remember I told you I have filters and I apply on the image, right? Now, what are the values of that filter? Because in image processing, we know the values. For example, I want to do edge detection. Let me add a page because I think it's very interesting. After this point, I will conclude the session. So assume my filter is 3 by 3. Assume I say 1, 1, 1, minus 1, minus 1, minus 1, 0, 0, 0. What does this do? I applied on my image. What does it do? Basically, what is it capturing? It says that I want my left hand, so my center point is here, right? Left of that, I want to be bright, maybe. And back of that, I want to be not bright. So basically, because minus 1 times that smaller value, plus 1 times that greater value, right? So luminance of the image. Basically, it means that capture the vertical edges, right? The vertical edges. Why? Because if I apply this filter here, it becomes big, because the small minus 1s are multiplied by the small values and plus 1s are multiplied by great bright values. So it becomes a big value, right? So this is good for capturing vertical edges, right? What about horizontal edges? I think you can guess now, right? Can you tell me? 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus. Or the other way around. Minus 1, minus 1, minus 1, 0, 0, 0, 1. I think it's called Prewitt filter. We have also another filter, which is Sobel filter. So people at that time used to tweak these values and publish papers. For example, they changed this to 1, 2, 1, minus 1, minus 2, minus 1. They called it another filter. Okay. So we have Sobel filter, Prewitt filter, and these things. So, and also what happens if I use this filter? You want 1, 1, sorry. You want 1, 1, 1, 1, 1, all ones. Also, yeah, I can have 1 over 9 times all of these, or just I can have a scalar multiplication all on the pixels as well. Doesn't matter. What does it do? Basically, it means that replace every center pixel with the summation of all of its neighbors. What does it do if I do that? It smoothens the image because it replacing every pixel with average of its neighbor. So it smoothens the edges and everything. It's like it becomes some kind of similar to fog. Put a fog on the image, it becomes a bit smoother, right? So it's for smoothing. You can have different ways to do smoothing. You can make it Gaussian. So in the center, let it be bigger, and the other parts let it be a bit smaller, like half. Or you can make it larger, and here 0.3 points. It becomes like a Gaussian distribution, right? That also smoothens your fun, because I think it's obvious, right? Gaussian at the peak, and it takes the average of everything in the neighbor. Now, so in image processing, it's obvious. We put things and we get what we want. In convolutional neural network, we also have filters, right? What do? Do we have the filter values? So how do we determine them? That's exactly the goal of neural network. Let's learn the filters. So how is convolutional neural network different from simple image processing? In simple image processing, you give the filter to me, I apply it. In convolutional neural network, it is machine learning. It says, let the machine decide what the filters should be for my task. For example, I want to do classification. What filters should I choose to do the task of classification, to extract important features for that task? Let it be decided by the backpropagation, by optimization, right? So I optimize the values of the filter. So I think even before the era of the convolutional neural networks, people would thought of that. So they said, why do we use manual filters? Let's find adaptive filters, or let's find the values of the filters. Nowadays, we do that by convolutional neural network. We find the values of the filters by optimization using convolutional neural network. Do you get it? And in this way, in different layers, as we saw here, in different layers, we extract different features. Also, in each layer, we have several channels. So we have several filter kernels. So in each layer also, we extract several various features. And how do they work? They kind of collaborate with each other in this way that, for example, one filter captures the edges on the right-hand side. And then the other filter kernel says, okay, you learned that. I don't learn this redundant feature. Let me learn some feature in the bottom corner, right? So each of these take care. So we divide the responsibility between several features, and they capture different features, and collaboratively it works well. It becomes a monster, right? So that's the philosophy of CNN, and we'll continue in the next session. Okay, thank you.